Stanford University.
All right, let's get back to SU3 and SU2. SU3 was QCD, and it's the symmetry which, what did we say? It acted vertically on our table. It took us from one color, red, green, and blue, and mixed them up. Let's just remind ourselves about that. So we made ourselves a table. This is a table not of all elementary particles, obviously, but it's a table of all the fermions. Yeah, it's a table of all of the fermions in the Standard Model, and not so much because they're fermions, but just it happens that they're kind of the constituents, the constituent particles of the atom and the nucleus. All right, so let's just write them down again. There were the 6 different families of quarks. The families refer to, well, I'll tell you what they refer to. There's the up and down. That's called a family. That's called the up-down family. Then there is up, down, charm, strange. I guess you can call it the charm or the strange family. And then there's the top and the bottom. That's the horizontal structure. And then we have red, green, and blue. And we have a quark in each one of these slots. Let's take this bar away here. Take this bar away and take this one over here away. We have a quark in each one of these slots. And the color symmetry, the SU3 symmetry, color, which is associated with quantum chromodynamics, is the symmetry group which acts on this triplet here and mixes them up into each other. That symmetry group has generators. Those generators correspond to the infinitely small transformations, but it also corresponds to the gluons. The symmetry group, which takes red to green to blue, is associated with the existence of gluons, and the gluons, when they're emitted from one quark to another, for example, from red to green, you create a red-green bar gluon. This transformation from red to green is simply one of the generators of SU3. So the generators of SU3, the transformations, are in one-to-one correspondence with the emission of a gluon. You can think of an emission of a gluon as a physical act, or physical phenomenon, which does the same thing as the symmetry group which mixes the particles into each other. That's the character of gauge bosons. Gauge bosons are a sort of manifestation of the symmetry group in which the emission of a gauge boson really does change a particle from one thing to another in exactly the same pattern as the symmetry group would change one thing to another. All right, so that's red, green, and blue. And when you perform one of these transformations, you do it on all of the quarks simultaneously. You don't do it just on the up quarks or just the up-down family. If you want the symmetry to be correct, if you want it to be a real symmetry of the theory, then you must do it simultaneously on all of the quarks, and that corresponds to the statement that exactly the same gluon, let's say this is from up to up quark to up quark. Incidentally, the gluon emission does not change horizontally. It only changes vertically. So, for example, the same gluon which would be involved in emitting, or which would be emitted when a red up quark becomes a green up quark, that's exactly the same gluon as would be emitted when, let's say, when a top red quark would be a top green quark. Red, green bar, gluon. All right. So the symmetry takes whole rows and mixes them into each other. Then there is a second symmetry. By now it's actually a third symmetry. We've talked about electrodynamics and what it does to the what the emission of a photon, or what the symmetry associated with electrodynamics is. But now we're encountering another symmetry, which is usually called flavor symmetry. Flavor symmetry, or I guess family symmetry sometimes. It takes ups to downs at the same time that it takes charm to strange, at the same time that it takes top to bottom, keeping the color unchanged. So, for example, there will be processes in which an up quark, let's say of the blue variety, emits a W plus boson, that's W plus, and it becomes a down quark also of the blue variety. So what has this W boson done? It's a physical manifestation of the transformation which takes you horizontally back and forth. Exactly the same W plus would mediate, or would be emitted, the same kind of W plus would be emitted when a green, let's say, charm quark becomes a green strange quark. Same W plus. And so forth. The gluons never move you horizontally. The W bosons never move you vertically. And that is also the character of the symmetry groups. The symmetry groups move you horizontally. That's SU2. It doesn't move you from here to here, or from here to here. It just moves you between up and down and up, or at the same time charm and strange, strange to charm, and so forth. That's the mathematical structure of SU3 cross SU2. If you add the photon emission is associated with the symmetry which changes the phase of every charge-carrying field, which I explained that to you last time. Every charge-carrying field transforms with a phase under U1. And if you add those three together, you have the basic ingredients of SU3 cross SU2 cross U1. Cross simply means that it's a product structure where the SU2s don't mix up the colors and the SU3s don't mix up the upness and downness. Well, it's a product structure, and that's where the terminology, that's where the I guess you would call it terminology, that the Standard Model is a gauge theory based on the gauge group SU3 cross SU2 cross U1. Now, it is actually a little bit more complicated than I'm saying. We're going to sort out the complications, but roughly speaking, SU3 for color, SU2 for the W emission, and U1 for electrodynamics. Now, this is it's going to get slightly more complicated than that, because what I'm saying is not 100% consistent for reasons that will become clear, but not yet. All right, the emission of a W boson, incidentally, of course, W bosons were only discovered relatively late in the game, and they were postulated sometime in the 60s, but it really only achieved some real traction in the 70s. the W bosons, but the theory of weak interactions goes, or some aspects of the theory of weak interactions, goes back much earlier than that, I suppose to the 30s, the Fermi theory of weak interactions, and we'll discuss the relationship soon enough. Okay, what about the coupling constants that are involved in these various interactions? The U1 coupling constant here, that's associated with the emission of a photon. And the coupling constant is simply the electric charge. The reason that the emission, or the reason that the probability of the emission of a photon is the fine structure constant is because this is the amplitude for the emission of a photon. You have to square it to find the probability for the photon to be present. So E squared is basically the fine structure constant. It has some pi's and things, it's not important, but E squared is basically the fine structure constant, and it's also the coupling constant or the emission, the quantum mechanical amplitude for the emission of a photon, either the virtual emission of a photon, which means that the photon is going to be reabsorbed before it gets very far, or if the electron is jerked out of the way, then the real emission of a photon. The amplitude for that is this constant called the electric charge. And it's a pure number, and it's a number, well, the fine structure constant itself, the square of this number, is, as I told you, about 1 over 137. Okay, so it's a small number here. The SU3 coupling constant, that's usually called G, or we can call it G strong, G sub S. That, of course, is associated with the emission of a gluon. And that's also a number. That number is close to 1. Well, not close, that's a little, 1 is a little bit too big. The corresponding thing corresponding to the fine structure constant would be more like about a fifth. A fifth is a lot bigger than a 1 over 137. So the emission of a gluon is a much, much more probable event. When a quark smacks into something, it basically emits a gluon with a probability close to 1. Almost always emits a gluon, whereas the photon almost never emits a photon. Now you might think, in view of the fact that the weak interactions are called weak interactions, and in fact, from the fact that the decay rates are very much lower associated with weak interactions, the weak interactions are indeed, in many, many ways, very much weaker than either the gluonic interaction or the electromagnetic interaction. But it's not because the coupling constant is smaller. The coupling constant of the weak interactions is closely related to the coupling constant for quantum electrodynamics. It's about the same order of magnitude. It's related by some simple numerical factor, but not very different. And so that raises the question, what is it about these processes involving W bosons that makes it so improbable, so unlikely that a weak interaction will take place? And it is unlikely, after all. It takes the neutron 12 minutes to decay. It must be a very unlikely process. So that's the next question. Let's think about the decay of the neutron. The decay of the neutron originates from a down quark inside the neutron, down quark emitting a W minus and becoming an up quark. So let's add in the other quarks. There's another down quark and an up quark. All right. This is a neutron. This is a neutron, an up and 2 downs, and this is a proton, 2 ups and a down, and a W goes off. Right? That's W minus. But then the W can also become, W minus can become an electron and an antineutrino. Let's go back to this table here. Let me remind you, there are more particles, more fermions. The additional fermions are the leptons. The leptons come in basically the same pattern, up, down, charm, strange, top, bottom, but they do not carry color. The meaning of that is they don't participate at all in the color interactions. Now you're perfectly free to ask me why, and I'm perfectly free to say I don't know. So, however, there's a pattern, and the pattern is not, it does have some structure to it. But I'll tell you what, not tonight, but at some point, maybe we'll understand this pattern better. Almost as though it were a fourth color are the leptons. Now, the leptons do not have the same charges as the quarks. Let me just remind you, this column would be the quarks with charge 2/3, and this column would be the quarks with charge minus 1/3. And notice that this one has one more unit of charge than this one. The difference of charge is 1 unit. All right, down in this lepton row over here, the same is true over here, of course. 2/3 minus 1/3, 2/3 minus 1/3. Now, the emission of a W only cares about the difference of charge. In other words, a W can be emitted if the difference of charge is the right thing. All right, the W plus or the W minus has a definite charge, and to emit it, the difference of charge of the initial and final fermion must be correct. All right, so if the W can be emitted when a neutrino becomes an electron, or when it becomes an electron becomes a neutrino, the charge difference must be the same. Okay? In fact, what goes down here would be the neutrino, the electron neutrino, and the electron. The charge difference is the same. This has charge -1, this has charge 0. So the charge difference is the same, and it is mathematically consistent to say that a W boson, the same W boson, can be emitted when a neutrino becomes an electron. Okay. In the next column, under the charm strange column, comes the neutrino associated with the muon and the muon. The muon is in every respect, at least as far as we know, essentially the same as the electron, except its mass is about 200 times larger. Again, no rhyme, no reason for that at the present time. And then under the top-bottom column, the heaviest of the quarks is matched with the heaviest of the leptons. Incidentally, we don't know the details of the masses of the neutrinos very well. All right, there's the neutrino associated with a tau lepton and the tau lepton. And the tau lepton is quite a bit heavier than any other lepton. Lepton, I understand. I don't remember right now what the word lep in Greek stands for. What is it? Light? Not heavy. Right. Oh, and baryons stand for heavy. Yeah. And mesons stand for something in. That's right. Meson. Okay. The terminology historically was a little bit confused. Mesons meant something in the middle. Baryons meant something heavy, like protons and neutrons, and leptons meant something light. Well, because of that, the muon was called the mu meson, because it was sort of midway between the proton and the electron. That terminology went away when it was realized just how different the muon was from the pion, which has a comparable mass to it. It was much more like the electron than it was like the pion. And so mesons are now reserved for quark-antiquark pairs, and they're always bosons, and the muon is no longer ever called the mu meson. So that's just a historical note. Okay, now, what is the probability of this process? It's a Feynman diagram. Every Feynman diagram has some parts to it, and the parts consist, first of all, of vertices and propagators. Propagators are the elements which have to do with the motion of a particle from one point to another. In this particular case, the motion of the W from the point where it's emitted to the point where the electron neutrino or electron antineutrino are created. Okay. All right, so this process has two main ingredients that we can isolate from the rest of it. One of them is 2 powers. Let's give the coupling constant a name. The coupling constant for the emission of a W, let's call it GW. G either for W boson or for weak. The QCD, the strong interaction coupling constant for emitting a gluon, we called G strong. This one is G weak. As I said, it's a number about the same order of magnitude as the electron charge. So it's not enormously small. It's not the smallness of this coupling constant which accounts for the improbable nature of weak interactions. All right, so first of all, we get 2 powers G weak squared. That's analogous to the 2 powers of electron charge if we exchange a photon. This is expected to be a number of about 1 over 100. It's not exactly the fine structure constant. You know, it's within a factor of 3 or something. It's close to the fine structure constant, order of magnitude. That's what this is. But then there's something else. There is the propagator of the W boson. So we have to know a little bit about propagators in quantum field theory. They are the factors which are inserted into a Feynman diagram to account for the motion of a particle from one point to another. All right. As such, they are simply functions of the space-time difference, or the space-time distance between the emission and absorption. They're functions, if you like, of the magnitude or the proper time along between this event and that event. But in any case, they're functions. That propagator, let's call it delta. Delta for distance between the 2 points. It's a function of the space-time distance between those points. Function of distance. And it has the following property. It depends, crucially, on the mass of the particle that's being exchanged. It depends on the following way. If we were to plot it as a function of distance, now, if we went through all the mathematics of quantum field theory and worked out the propagator, we would find that it's got a lot of stuff in it. It's got Bessel functions. It's a kind of complicated function, but not that complicated. But the important aspect of it is that it is large at small distances. It falls, or it grows like 1 over the distance to some power, 1 over the distance squared between the 2 points. Right? So it's very large at small distances. But then, and if the particle had no mass, it would just continue on its way with the same power law fall off. It would just fall off gradually with one universal behavior, which would go like 1 over the square of the distance between the points. That's the way it would behave. But the mass of this particle introduces a new ingredient. It introduces an ingredient which causes the propagator to decrease suddenly like that. It decreases exponentially fast. Exponentially fast. In other words, the power law gives rise to an exponential. And the interesting question is, where does that happen? Where does that happen? At what value of distance does the mass suddenly manifest itself and tell the particle, hey, you're out there and you shouldn't be out there because you're carrying off mass and there's no mass to carry off. I mean, you're carrying off some mass from and there just is none. You've got to get back there. You don't have to think about it in terms of a story. The propagator has an exponential decrease. Where does it happen? And the answer is just dimensional analysis. In units in which C equals h bar equals 1, pick such units. Mass has the same units. Now, when I write m equals, I simply mean units. What's the usual notation for units? To put a square bracket around the quantity? Okay. The standard notation for the units of an object is to put a bracket around it. A mass has the same units as an energy. Well, why is that? That's because E equals mc squared, and if C is equal to 1, et cetera, et cetera. But they also have the same units as inverse length. Mass has the same units as inverse length. Or, incidentally, there's a third quantity which has the same units of mass and energy. What is it? Momentum. Same as momentum. Now, what about momentum times distance? What are the units of momentum times distance? No? Think uncertainty principle. Think uncertainty principle. Momentum times distance is h bar. But h bar is dimensionless in these units. So momentum and distance simply have inverse units to each other. Okay? So therefore, length has inverse distance to both mass, energy, and also momentum. And therefore, we can say that, we can write it differently. We can write that length has units of inverse mass. Yeah, 1 over mass. Well, that tells us the horizontal axis here was distance, d. The mass of the particle is m, and that tells us that the distance at which it falls off like this, the only way that we can make a distance using the mass of the particle, occurs at a distance of 1 over the mass of the particle. Now that's really the Compton wavelength of the particle. If we put back some C's and H bars, what would it be? H bar over MC? Let's put back the H bars and H bar over MC. Distance at a distance of order H bar over MC, the propagator suddenly dives down and as an exponential. The vertical axis is the size of delta. Delta. And what it is its square of the propagator is the probability that the particle can go that far before it emits. Right? So what this is saying is that there's a sudden sharp turnoff of the probability for the particle to go a given distance before converting like this, which is controlled by the mass of the particle. In particular, the heavier the mass of the particle, the less the distance it can go before it has to give up its energy in this form. All right, now, usually what's prescribed in an experiment is not the 2 points where these events take place. What's prescribed in an experiment is the momenta of the particles. You measure the momentum of the particles. You measure the momentum of the incident particle, P of the proton. No, this is the neutron down here. Neutron. You measure the momentum of the proton. And what do you know? You know the momentum of the W boson. The momentum of the W boson is the difference of the momentum of the proton and neutron. So you know the momentum of the W boson. And of course, that tells you the momentum of the electron and neutrino by momentum conservation. You don't, as a rule, well, certainly not in these kind of experiments, actually know the distance between those 2 points. You know the momentum. But there's a relationship between functions of momentum and functions of position, or functions of distance. And that relationship is Fourier transform. You can think of the propagator either as a function of positions or momentum. You can think of it as a function of either position or momentum, the position distance between here and here, or the Fourier transform of this function. The Fourier transform of it is the amplitude for emitting a W with a given momentum. So the question is, what does the Fourier transform of a function like this look like? I'm not going to work it out. This is something you can go and study for yourself. A function which has a power law and then a sudden decrease like that. I will simply tell you what the Fourier transform of the propagator is. The Fourier transform is a function of the square of the momentum of the W boson, and also parametrically it depends on the mass of the W boson. Let's call it delta twiddle. Twiddle stands for Fourier transform. And it's a function, what shall we call the momentum of the W? Let's call it K. And what does it look like? It's very simple. 1 divided by K squared plus the mass of the W squared. That's it. That's the factor. That's the factor that you put in if you know the momentum of the W. And how would you know it? By measuring the initial and final momentum of the proton and neutron. You measure the momentum of the W, and then you insert this factor in as one of the factors into the amplitude for the emission of the W. That's the rule. That's Feynman's rules. And that's it. The addition, first of all, let's talk about a photon. If we emit a photon, it has no mass, and it's just 1 over K squared. Typically, when you emit a photon in ordinary quantum electrodynamics, the momentum of the photon is pretty low by particle physics standards. It's typically, a few hundred electron volts or something like that. It's a very small K. And so the propagator for emitting the photon at low momentum is rather large. At low momentum, this is a big number as K goes to 0. The weak interactions, we know that the probability of emission is much, much smaller. As I said, it is not the coupling constant there. So the only thing it can be is the mass of the W boson. If the mass of the W boson is very large, for whatever reason, then this is always going to be small. In fact, the biggest it will ever be is what happens when K is equal to 0. When K is equal to 0, this propagator here is equal to just 1 over mw squared, and it's never bigger than that. That's as big as it gets. So the most likely thing to happen is to emit a low momentum W. And if you do, it costs you a probability amplitude equal to 1 divided by the mass of the W squared. This is standard quantum field theory. In addition, there are the coupling constants. So the net result is that the probability, or the amplitude, not the probability, the amplitude for emitting a W and having it convert to an electron neutrino is GW squared divided by MW squared. The mw squared is the factor in this Feynman diagram for the w to go from here to here. Or at least that's the biggest it can get. Yeah. Question?
With regular propagators, the k squared part has minus signs in it. K naught squared minus k1 squared.
Well, yes, this is true. This is true. Where, okay, so there we have to get a little more technical. And that mostly comes into play. Yeah, very little energy is emitted in a situation like this, and more momentum than energy. So it's mostly space-like, which means it's positive. For a reaction, you would have to worry about this if the momentum of this was time-like, but it's not in these kind of processes. But still, the main thing is that it's always small. Why is it small? A proton becomes, in a beta decay, the amount of momentum that's transferred from the proton to the, or from the neutron to the proton is minuscule by comparison with the mass of the W boson. Minuscule. So it doesn't even matter whether it's positive or negative, the k squared. It's tiny by comparison with the mass of the W. So the net result is that the weak interactions are made weak because of the large mass of the W. How large is it? About 100 times the mass of a proton. Right? So that means that, that the amplitude for this process is going to have a factor, a relatively small factor from GW squared, roughly the fine structure constant, and then a 1 over mw squared, which is a tiny fraction. It's squared. The mass of the W is 100 times the proton mass. That's a factor of 10,000, but that's just the amplitude. We have to square the whole thing to find the probability for the reaction to happen. So what does that mean? That means something like GW to the fourth divided by mw to the fourth. That's a very small number. That's a very small number if the mass of the W is large. That's why weak interactions are small. Not because the primordial coupling constant is small, but because the mass of the W, for whatever reasons, happens to be large in nuclear physics or in proton, neutron type mass units. In the usual units of nuclear physics or old particle physics, the mass of the W is large. Yeah.
Were you just saying that like 1 in a million or like 1 in a billion?
It wasn't. Well, GW squared is about 10 to the minus 3 or something, and then the mass of the W is 100 in proton units, so that's 10 to the 4 millions at least. More than that, yeah.
How do we know what the mass of the W is?
From the weakness of the weak interactions. Right. So, right. So originally, all that was known from experiment was this combination. What was known was that combination, and it was called capital G Fermi. Experimentally, what you measure is neither, by now, of course, there are fancier experiments, but the experiments in the old days, where you never had enough momentum to make this denominator vary very much, you didn't get to see that the denominator was varying with momentum, all you saw was this numerical constant. And it was always the same W boson in there. It didn't change from one reaction to another. It was always the W boson. It was always mw squared. And so experimentally, all you knew was this number G Fermi, which is a small number, okay, a very small number, whatever its numerical value is. It carries dimensions. So if I told you what it is in some, what should I tell you, in units of light years per unit, whatever, it's a small number. Right. So that's what was known historically. Sometime in the must have been in the 1950s, various theorists, Julian Schwinger, other people began to suspect, look, maybe the weak interactions are similar to other interactions and mediated by some sort of particle. I don't know where the terminology W came from. Probably stood for weak, and I don't know if it was Schwinger or not who first used it. But the idea of a particle heavy enough that it would make this a small number was introduced sometime, I think, in the 50s. But it was recognized pretty much from the beginning that it would take a pretty heavy particle, 100 times the mass of the proton, and so it wasn't until accelerators came into being where you could generate that much energy, in the mid-70s, late 70s, where accelerators, which could create enough energy to generate a W particle, actually detected it and actually measured it. So yeah, the W particle really exists, it can be produced, and yeah.
So at the beginning of the class today, you talked about the effect of the binding energy, which seems to me in this picture is the presence of the field of a nearby proton that suppresses this whole process.
What suppresses it?
The presence of the field of the nearby proton in the deuteron. In other words, it's
It
not
only suppresses it because of energy conservation, nothing else. A thing can't happen if there isn't energy available for it to happen. So that's another thing which controls rates. Yeah, okay. Rates are controlled by three things. Three things. Coupling constants, masses of particles in intermediate states like this, and also available energy. Available energy has to do with the energy of the initial state and the final state. There are three different features: coupling constants, masses or propagators, if you like, the structure of propagators and how they depend on momentum, and finally, a thing can't happen if there isn't enough energy, and it will happen with very small probability if the energy available is small enough. So you need the initial state to have as much energy as the final state in order for the process to happen. And it's the last of the ingredients there that had to do with the suppression of the deuteron decay. Three separate things. Yeah.
These coupling constants, are they really constant, or do they vary a little bit?
They vary a little bit with, and we will come to that, with momentum, with distance scale, yeah.
So the W boson has a lot of energy, right? A lot of mass.
Well, a real W boson in the laboratory has a lot of mass.
Now, when it degrades into an electron and a muon,
Yeah,
whatever, right? What happens to that energy?
No. The energy of the final state must be the same as the energy of the initial state. That means there isn't really enough energy to create the W boson. There really isn't enough energy to create the W boson. That's why there is no real process in where a W boson goes flying off. There simply isn't enough energy for that. Well, so what does happen? The W boson is produced virtually. According to the rules of quantum mechanics, a violation of energy can take place as long as it takes place for a short enough time. If the amount of extra energy that's in here, let's call it delta E, energy time uncertainty principle, says, among other things, that an apparent violation of energy conservation, delta E, can only last for a time, delta T, which cannot be bigger than, which must be smaller than in this case, Planck's constant. You cannot have an apparent violation of energy in an intermediate state that lasts for a time longer than delta E, delta T of order h bar. Let me give you another example of this sort of thing. if you have a potential, ordinary potential energy, this potential energy could be the potential energy of an alpha particle in a nucleus. An alpha particle is stuck in the nucleus, it can't get out. Why not? It doesn't have enough energy to get out. It has to go over a bump to get out. So the alpha particle normally sits over here, but it can tunnel out. Quantum mechanically, it can tunnel out. Now, the kinetic energy of a particle is always positive, right? In here, it has a certain amount of energy. It has a much higher potential energy over here. This is a potential, an ordinary potential function. The potential energy is up here. The particle started at rest. It had no kinetic energy, and it had this much potential energy. It has the same amount of potential energy over here, and the same, and also when it comes out over here, it also comes out at rest. Comes out over here at rest. It was at rest over here, same potential energy, same potential energy. So it can happen. On the other hand, if you look at it in between, it seems that it had a large potential energy, much larger than it had over here, and it can't have less kinetic energy than it had over here. The kinetic energy was zero over here. The meaning of that is that it temporarily, apparently violated energy conservation. Now, if you went and measured the particle in here and checked whether it was in here or not, you would destroy the phenomena of tunneling. But if you just look on the outside, you will have to say somehow in the intermediate state here, the electron had more energy than it was, or the alpha particle had more energy than it was supposed to have. There was a violation of energy conservation, an apparent one. How long can the alpha particle last under this barrier here? The answer is it can't last long, and the rule is if the violation of energy conservation, this over here, delta E, then it had better get out from under there in a time delta T, which is less than h bar over delta E. All right, so this is a kind of familiar thing from elementary quantum mechanics, that apparent violations of energy conservation can take place as long as they last sufficiently short time. Same thing over here. The W boson is a very heavy particle. There is simply not enough energy in the proton, neutron, or anything else to create a W boson, let alone have enough energy for the final particle. That cannot happen. What can happen is that temporarily, for a very, very short time period, the neutron can emit the W minus, become a proton, but then it is as if the alpha particle were under the barrier here. The W boson says, I can't last that long, I better get rid of all that energy, and it can do it a number of ways. One way it can do it is just by getting reabsorbed. Okay? The other way it can do it is by becoming the electron, which has a small energy, and the antineutrino, which also has a small energy. So the intermediate state here of a very, very heavy W boson is very much like the intermediate state in which the alpha particle is under the barrier here. And it can only last a short time, yeah.
Is there any way that any other things like electron number can be temporarily or virtually?
No. And even energy conservation from initial to final state is always exact. It's just an apparent violation.
It would appear as though the reabsorption is what happens all the time. That basically, the W comes out, goes back, goes out.
Most of the
back.
times that's what happens.
Every once in a while, every once in a billion tries, it goes out far enough
Right.
to
That's
decay
correct.
itself.
That's correct.
And
That's correct. That's correct. Most of the time, it doesn't.
Do we have accelerators that are powerful enough to make real W bosons?
Yeah.
How long?
Yeah. Now, the Ws will decay to electrons and neutrinos, But if you make a W with enough energy, all right, there's a certain lifetime for a real W to decay. It's not this uncertainty time here. There is a certain lifetime, so the W, when it's produced, will eventually decay. But the faster the W is, the more time dilation will cause the W to decay later and later. So real Ws are produced, and the meaning of real Ws is that you produce things whose decay probability is controlled by their velocity in the standard relativity way.
What's the proper time for it to decay?
Oh boy, okay. Very short. Very short. The W. 3 times 10 to the 27th? Is that true? I will have to think about it.
You've described the Coupling constant as the probability. You've said the Coupling constant is the probability in that diagram of the W.
Well,
being,
okay.
but how does that translate into a rate or a time for the decay? I mean,
The rate, right? This is the amplitude. All right, this is the amplitude for the process. The square of the amplitude is a probability. That's this. And it's a probability per unit time. It's a probability per unit time. And so its inverse is related to the lifetime. Its inverse is related to the lifetime, and that's why this is a very small number. The lifetime is unusually large in particle physics units. So weak lifetimes, particles which can only decay for one reason or another by weak interactions, have anomalously long lifetimes. And where do you trace it to? You trace it to the mass of the W. Now, if a process, remember what this really was, it was k squared plus mw squared. Right, if you have enough energy and enough momentum, you can detect the fact eventually that these rates here will be momentum dependent. In other words, the effective constant here won't be constant, it will depend on k. And that, of course, has been seen with great precision. So,
For the tunneling process, there's a delta t which applies a kind of velocity. Is there a...
yeah, but if you went in there and tried to detect the velocity, you'd destroy the process. So,
If you take this end and that end and figure out the delta t, the distance, you can infer it.
you can construct something you can call a velocity. It would be misleading to think of it as the velocity of a real signal, though. It's not a signal velocity.
Can we usually get any understanding of the lifetime of a free W from looking at the Coupling constant?
Mm-hmm. That's exactly the way you would calculate it.
Because a shot is so short. Because the Coupling constant.
The W boson, for example, it has a number of ways of decaying, but one way it can decay, literally decay, is into an electron and an antineutrino. And you can calculate the Feynman diagram describing, it has this factor G in it. W minus a factor G and electron and antineutrino, and you can calculate that. And yes, you can compute the lifetime of the W. Whatever it is. You can estimate it, but yeah.
Same twist on the question. In the case where in the laboratory you produce a W boson,
Right.
what happens to that energy? Because the electron has very little energy.
No. The W, when a real W decays, it produces an electron and neutrino with enormous kinetic energy, very relativistic, right? It does, a W boson at rest will become, and there are other decay modes. I mean, this is not the only decay mode. It can do a muon in a neutrino, a number of different decay modes. But if it decayed to an electron neutrino, they would be very, very relativistic electrons and neutrinos. Now,
I'm a little confused with exactly what is the distinction between a real and a virtual particle. Is there a clear definition? Is there a gray
real and
area?
virtual, real particles are simply the ones in the created initially, well, the particles which came in and particles which went out of a small interaction region. The virtual particles are mathematical constructs which are the internal particles in a Feynman diagram. You don't observe them. If you went into the, if you suddenly tried to observe that particle, how would you observe that particle? The only way you could observe it would be send something else into the system. Okay, let's talk about trying to observe particles of this nature. Or even before that, what about trying to observe what's happening to an alpha particle as it moves under there? Well, obviously you have only a very short time to observe it. So if you want to observe, if you want to know whether there was a particle under here, you would have to interact with it on a very, very short time scale. Right? You would have a very short time scale to get in. If you wanted to find out, for example, by looking at it with a photon, you would have to send in a very, very short wavelength photon pulse. In particular, the energy of that photon pulse would have to be about that big. That's what this energy time uncertainty principle says. The same energy time uncertainty principle gives you information about the wavelength and the energy of a photon that you would need if you wanted to have a time resolution good enough to see what was going on in there. All right, so if you wanted to actually see the motion of the alpha particle from here to here, which lasts a time delta t, you would have to hit it with a photon whose energy was big enough that it actually would knock the alpha particle into this region here. You're supplying the energy, and it's one of these quantum mechanical complementarity things that you think something is impossible, and so you try to detect it. And you find out in order to detect it, you have to do to the system exactly that thing which you were trying to prove does not happen. Right? Right. This is quantum. It's always the same story. And the same would be true of virtual particles. Virtual particles last a small time. If you wanted to get into the system and detect one, you would have to hit it with something with enough energy that it would actually create that particle. If you wanted to see the virtual W here, how much time do you have? Very short. So you hit it with a photon of sufficiently small wavelength that, guess what? It's got enough energy to actually knock a W out of the system so that you actually see a W. All right, that's sort of unsatisfying and frustrating. You were trying to prove one thing, and you found out that you had to do something to the system which did to it exactly what you were trying to prove didn't happen. It's always that way. That's quantum mechanics in a nutshell.
Isn't it true that in a part of a physics experiment you never see directly the W? You never, on a scattering experiment, you never see a W.
Not true. Not true. If you're trying to see, for example, okay, so let's first talk about something slightly different. Do you ever get to see the virtual photons that are present in an electron? Well, yeah. If you hit the electron hard enough, you'll knock out, or you'll knock the electron out, and the photon will be left over. So you do get to see them in that sense. You do get to see the virtual photons if you do exactly the experiment which puts in enough energy to see those virtual. Well, let's come now to the W. Same thing is true. If you have a proton, that proton can emit a W and become a neutron. And of course, if there's nothing else around and it doesn't decay, then the W will have to come back and be reabsorbed. And so you can think of a proton as a sort of equilibrium between a proton and a neutron with a W boson around it, constantly going back and forth between the two of them, between the two things, with a very, very, very fast oscillation, an enormously fast oscillation between the two. You want to see that W? All you have to do is hit it hard enough with a photon that has a frequency which is large enough that it can resolve the short times that the W is out there. And guess what? If you do hit a proton with a high-energy photon, yes, you will knock out a W. So in that sense, you get to see them. But then, of course, it becomes a different process. It becomes a process in which the W is a final particle, not an intermediate one.
Is there any sense to saying that there's a different...
I think somebody...
Did you mean to exchange neutron and proton in that?
And when proton goes to neutron, goes to proton. You can also have neutron goes to proton, goes to neutron with a W. The difference is that this one would be a W plus and this one would be a W minus. Yeah. Yes?
Does it make any sense to say that when you did that experiment that you knocked the W particle out as opposed to you created the W particle?
No, you can say it either way. Yeah. Language is one thing, facts are another thing. The fact is, at the end of the day, there will be a W flying out. Do you want to interpret that as a W that was there beforehand, that you knocked out, or was it a newly created W? Well, the mathematics says that there will be a W there. One picture of it is that the W was there, and you jerked the neutron out before the W had a chance to get back. And the mathematics supports that. I mean, that there is a way of thinking about the mathematics that says that that's what happens. Yeah.
On the other hand, is this true that if you all you ever get by putting enough energy is W particle? You don't get some other kind of particle.
You don't get what?
Well, if I put in enough energy to get a W particle,
Yeah.
I get a W particle. What if I put in twice that energy?
You still get W particles.
So
You get W, but you
doesn't
get-
that imply somewhere in existence the W, because you always get W's?
Well, you don't always get W's. Sometimes you get W's. Sometimes you get W's. Sometimes you might get 3 W's. Sometimes you may get... When you hit a particle hard enough, you get all sorts of junk. When you hit a particle really hard, this is what I was trying to tell you the other night. You know, when you try to think about what is elementary and what's not elementary, it gets very confusing, because if you take what you thought was a very elementary particle and you hit it really hard enough, all kinds of junk comes out, and among the junk that comes out might be chairs and tables. Well, you'd need a hell of a lot of energy for that. But you hit an electron hard enough with a photon, really, really, really hard, meaning to say with much, much more energy than, for example, the mass of a proton, mass of 1,000 protons, for example. And guess what? Out of it will come protons, electrons, all sorts of things. Every once in a while, one of those electrons will stick to a proton. And so you will discover that inside an electron or inside a proton, there's a hydrogen atom. The lesson is, don't try to, your mental picture of what comes out of a system is necessarily what was in there beforehand is a little bit defective.
High energies.
Yeah.
Does this have anything to do with vacuum energy? Or is it-
This in itself doesn't. This in itself doesn't. The vacuum energy really has to do with diagrams which are disconnected from the rest of, they're just there in the vacuum. But the presence of vacuum diagrams like this, you know, okay, so a vacuum diagram is something which also apparently violates energy conservation. Let's suppose this were an electron, and a photon. 2 electrons necessarily have a certain minimum amount of energy. The vacuum has no energy, okay? And so there's a certain violation of energy in there. That means that that pair can only last for a short time. And I say, okay, I would like to see that pair. So you send in some very high frequency photon, or a pair of very high frequency photons from opposite sides, and guess what? You sometimes make electron-positron pairs with an extra photon in them. So you knock the hell out of that vacuum fluctuation, and you discover pairs of particles. Yeah.
Are these reactions, are they independent of temperature or dependent?
Oh, no, they're not dependent on temperature. They are dependent on the particles that you're colliding having a lot of energy. All right, so it's a good question. Let's say what it has to do with temperature. When you have a system at high temperature, it simply means that you have a lot of particles around with high energy. So that means that typically at high temperatures, there are enough high energy particles to cause these things to happen. But just think of high temperatures as just having a lot of high energy particles around. If you have a very small number of high energy particles, you won't think of that as temperature. You'll just say, I have some particles with large kinetic energy. Right? An example of what temperature can do is if you had the alpha particle bound inside the nucleus like that, and then you put it into a temperature bath. Now, I don't mean your bathwater temperature bath. I mean temperatures which are many MeVs high, which is zillions and zillions of degrees high. But the effect of putting it into temperature, you can either think of it as particles coming in and colliding, or you can just think of it as thermal vibrations causing this alpha particle to jiggle around, and give it enough temperature, and sure enough, it'll jiggle over the top sometimes. So yes, these virtual processes can be induced by temperature. But temperature is another way of just saying there's a lot of high energy particles around.
Did you say that the vacuum could not be attributed to the generation of the W plus the
The vacuum could
oscillation?
not be attributed, I don't think I ever said the vacuum was attributed to anything, but
No, it could, you were talking about the
vacuum fluctuations.
Yeah, vacuum fluctuations. The W plus is some kind of a fluctuation too, is it?
Well,
it
the W is
related
a
to
particle. The W is a particle.
that? I know, but isn't there a relationship between that and the?
The W in this diagram is a fluctuation, but it's not a fluctuation of the vacuum, it's a fluctuation of the proton. The proton sometimes fluctuates and makes a W and a neutron. That's, a relative of, but not the same thing as saying an electron, a antineutrino, and a W, let's see, that would be a W plus, can sometimes form a vacuum fluctuation. It's another process where there really isn't enough energy for it to happen, so it happens in this virtual sense for a short period of time, and in that sense it's similar to this, but it's different. But the same rules apply to it. It can only last for a short time. Therefore, if you want to get into it and observe it, you have to do it with something which has very high energy because of the uncertainty principle. And the result is the energy is always enough. If the energy is high enough to see in there, it'll also be high enough to create those particles. You'll have enough energy to actually release them.
The antineutrino is necessary for conservation of spin.
Say it again?
The antineutrino is necessary there for conservation of spin.
Yeah. Mm-hmm. But another way of saying it is that the basic interaction is always one between electron, neutrino, and W. Right. But yes, it is. Right.
I was thinking that you could turn a coffee bean into a cake.
You can cook a
Coffee bean into a cake, chocolate cake, by, basically adding energy. You put in enough energy to incinerate the coffee bean and add a chocolate cake.
Mm-hmm. Wow, just one chocolate? Why only one chocolate cake? Okay, so what's the weight of a chocolate cake? The weight of a chocolate cake is, if it's really good chocolate cake, dense, it weighs 1 kilogram, right? Right. A kilogram is 1,000 grams, which is 10 to the 8th Planck masses. Okay, 10 to the 8th Planck masses, that's right. If you could accelerate a pair of particles to 10 to the 8th Planck masses with a very, very, very small probability, you might get a chocolate cake out. Yeah. Dream on, Michael. What's that?
Or anything else that weighs a kilogram.
Or anything else that weighs a kilogram.
If you make the delta T small enough, using your chair analogy, you could get electrons turning into chair and anti-chair.
Right.
Now, if you take that to an extreme, the shortest possible time, what is the mass that would, like a Planck, unit of Planck time, what would the mass be equivalent to that?
Of a Planck time?
Yeah.
The Planck mass, which is about 10 to the minus 5 grams.
So wouldn't that be the limit to how?
No, the Planck mass is not the heaviest mass. Obviously not. I weigh a lot of Planck masses.
But if you trade chairs and anti-chairs, shorter time you could play planets and anti-planets and galaxies and anti-galaxies.
If you collide particles at energies much larger than the Planck mass, what you get, I was going to say 99 times out of 100, but let's make it 99.9999 endlessly out of whatever it is, you'll get a black hole. Okay? But every once in a while, with a probability which is exponentially small in the entropy of the black hole, that black hole will emit a chair instead. Right. How do I know that? I know that because the process of a chair falling into a black hole is possible, and therefore, by time reversal invariance, the process of a black hole emitting a chair must be possible. So yes, every once in a while, the black hole, or when I say every once in a while, I mean a very rare percentage of the times that you do this experiment, the black hole will behave in a statistically extremely unlikely way. But all that entropy is statistics, and basically anything that can happen will happen eventually. And so yes, everything can come out of a black hole if you do the process enough times. So so all of this above the Planck energy scale has to do with the properties of emission from a black hole.
The virtual photons and W particles are bosons. So will they interact with the other bosons in the close by and tend to fall?
Okay, which photons?
Virtual photons and virtual.
Will they interact with which?
Any other virtual photon.
Okay, the virtual, let's first ask, does the W interact with the photon?
Well, say there's another W close by that virtual W, if they were, will they fall into the same state as their bosons?
You want to know whether the W's will interact with each other. Is that the question?
Well, photons fall in the same state probabilistically, even though they don't really interact with each other. You know, at least
Well, photons do interact with each other a little bit. You know how they interact with each other?
through virtual pair production, but
Right.
I'm talking about due to the fact that they're bosons.
Wait, the fact that they're bosons is not what says that they don't interact with each other. Bosons, fermions, they all interact. No difference in that respect. The reason that the photon doesn't seem to interact with other photons, let's see if we can trace it down. Photons can scatter. Now, ordinarily in the laboratory, two light beams won't scatter each other. But two photons can do the following. A photon can come in, another photon can come in, and they can create an electron-positron pair. Electron, E minus, E plus, electron-positron pair. Well, if that can happen, then the opposite can happen. An electron-positron pair can become a pair of photons. And in fact, it can happen as a virtual process. As a virtual process, a pair of photons can come in, and go out, but scatter by means of an intermediate state, which is an electron-positron pair. Okay? Now, why doesn't it happen in the laboratory with ordinary photons? And the answer is it takes a certain amount of energy to create the electron-positron pairs, right? Each electron has a mass of, what is it, half an MeV? Right. So these together take an MeV of energy. If the pair of photons has energy very, very much lower than that, then there is not enough energy for the real creation of an electron-positron pair, but still it can happen virtually. But when it happens virtually, there are propagators in here, and it's the same sort of deal as what happened here. When you have to supply extra energy for the process to happen, there is always a cost in probability. Typically, the cost in probability is somehow inverse to the amount of energy that you need to make the process happen. Okay? So this process doesn't happen in the laboratory because in the laboratory, photon energies are always vastly smaller than the mass of an electron. Photon energies are what? An electron volt? Typical photon, optical photons are an electron volt or two. The mass of an electron is of order 1,000,000 electron volts. And so typically the photons don't have nearly enough energy for this process to happen. And when an intermediate process happens, which has to happen very fast, it comes and goes, it's always at a cost of probability. So this process, the scattering, is a very low probability process at low energies. On the other hand, if the photons hit with enough energy to be able to create an electron-positron pair, they really do interact with each other. Now, I forgot what the original question was. It had to do with W bosons. But the same thing is true. W bosons do interact with each other.
I wasn't talking about that type of interaction. I was talking about their statistical interaction because they're both...
Oh, they are bosons, yes. Don't think it's not an interaction. It's just the effect of Bose statistics. Well, let's put it this way. The effects of the statistics, fermion versus boson, is only interesting when you have a situation where you create more than one particle. So more than one particle pretty well near each other, pretty much in the same state. In most particle physics experiments, you create the particles going off, flying off in every direction, and it's very rare that you have two particles of the same type going off in pretty much the same direction in such a way that it matters very much whether they're fermions or bosons. But yes, I mean, they do interact statistically the same way photons do. W bosons will prefer to be in the same state, in the same sense that photons prefer to. In principle, you could make a laser arrow with them. Not likely, but in principle, you could make a system laze W bosons.
Can you tell whether
You should call it a laser.
can you tell what color a proton or a neutron is?
What color it
Does
is?
it matter? Red, green?
No, it's always 3 quarks, 1 red, 1 green, and 1 blue, which makes it white. Or colorless. Black or white, I'm not sure, but I guess white.
But there should be superpositions of red, green, and blue somehow. No?
But a proton is always 1 red, 1 green, 1 blue.
Is this a place to bring in what happens at the other end of the energy spectrum, like the Bose-Einstein condensate?
Well,
Is that, I'm just asking the question, is this a place to fit it in, or will we get to it?
yeah, we will get to it, and we'll get to it in the context of the Higgs boson. Yeah. The Higgs boson is the place where something like Bose condensation happens. All right, I did have one. All right. Nobody has asked me, so let me bring it up myself. What kind of group structure could we imagine which would mix the up quark and the down quark? Well, the up quark and the down quark. The charm quark and the strange quark, just forget them. Just up quark and down quark, they go into each other by W emission. What group could we be talking about? Now, it's obvious. We're talking about SU2. There are two elements here, and one can go to the other. That's the symmetry of the system. We're talking about SU2. But how many generators does SU2 have? Good. It has 3 generators. Each generator, the gauge bosons are in one-to-one correspondence with the generators of the group. That's the way it works. The 8 gauge bosons, the 8 gluons, there's one for each generator of SU3. We only have 2 gauge bosons, W plus and W minus, but we're trying to postulate that this is a theory based on the symmetry SU2. We're missing something. And indeed we are. We're missing one gauge boson. It is not the photon. It is not the photon. It is closely related to the particle called the Z boson, a third member of the W family, W plus, W minus, and Z. Okay? We'll come to it next time. Please remind me if I forget to talk about the relationship between electric charge, the Z boson, SU2, and so forth. We've got to come to that. But I wasn't, I was going to talk about it, but it's getting too late for now. In fact, it's getting too late to do almost anything. The other thing I had intended to talk about tonight was spontaneous symmetry breaking. Let's talk a little bit about spontaneous symmetry breaking, just qualitatively, and we won't try to do anything quantitative tonight, just qualitatively. What is spontaneous symmetry breaking? I think the best way to describe it is by illustrating it. There's a famous illustration, which is in a sense spontaneous symmetry breaking, but if it helps you, okay. It actually is somewhat correct. The famous example is people sit down to dinner and around a large table, and each person has to the left of them a fork and to the right of them a fork. Next person left of them and the right of them a fork. And nobody knows whether to go for the left fork, or the right fork. And they sit there and they sit there and they sit there, and they can't decide what to do until all of a sudden one of them makes a little motion toward the right fork, and then they all go for the right fork. There was nothing asymmetric to begin with, but there was a kind of instability. There was a kind of instability, 2 possibilities, an instability, and the instability being such that when the instability is kicked off, the whole universe, so to speak, suddenly goes one way instead of the other way. So I will give you an example, a mathematical example. A magnet is an example of spontaneous symmetry breaking. But let's start with a very simple example. The simple example is a bunch of spins, and the spins can either be the spins can either be up or down. For the moment, it's not even important that we're talking about quantum mechanics. These could be coins, classical coins, right? And the coins can either be up or down. They're laid out on a table in a lattice. Here they are. And there's an interaction energy between neighboring coins. The interaction energy is such that if the neighbors are opposite, for example, a heads and a tails, that cost energy. In other words, there's some kind of force between the particles or the spins or the coins, so that if they're opposite, that costs some energy. If they're parallel, it costs less energy. Okay? So they like to be parallel. Energetically, they like to be parallel. But parallel can mean this way or this way. Anti-parallel can mean this way or this way. Anti-parallel costs more energy than parallel. Okay? Now think about the state of lowest energy. What is the state of lowest energy? The state of lowest energy is obviously all heads or all tails. There are two states of lowest energy, all heads or all tails. Which one is the ground state? They're both ground states. But now, supposing way far away, off 100 miles away, one of the spins is known to be heads. That one is asymmetric. Well, normally, under most circumstances, you would say that 1 degree of freedom very, very far away has no effect on what the properties of the ground state are far away from that degree of freedom. That's a typical expectation. It's usually true. It's almost always true ordinarily. But in this case, that one head will cause the ground state energy to be different if they're all heads than if they're all tails. If they're all heads, then you'll save 1 unit of energy. And so in seeking its ground state, this system will tend to all heads rather than all tails. Once it's all heads, then you can forget, once it's all heads, then you can start over again and say, look, the lowest energy state of this system is all heads. It will cost me some energy to put a tail in there, because it has 4 neighbors which are trying to make it a head. So the result is that this kind of system, although it started with a symmetry, heads goes to tails, asymptotically very, very far away, boundary conditions, or just a very, very distant degree of freedom will tip off a instability and put the system into one of the many possible, in this case only 2 possible ground states. And once it's in that ground state, then the properties of what goes on in here are determined by that ground state. In particular, a tail will cost you energy because of the presence of all the heads. This is the simple and primitive, most primitive example of a spontaneous symmetry breaking. How is it different than just an ordinary symmetry breaking? What would an ordinary symmetry breaking mean? An ordinary symmetry breaking, or what we can call an explicit symmetry breaking, would be a symmetry breaking if heads had a different energy than tails. Not pairwise energies, but just one head by itself. Supposing that one head by itself had less energy than a tail, then of course it would be completely obvious that the system would, in its lowest energy state, be all heads. And so it would be also the case, all heads, but there would be no second ground state in which they were all tails. It would be biased by the energy, or be biased by the energy, not the one extra particle infinitely far away, but by the local things going on nearby. Okay? So that would be a biased situation where heads and tails were not equivalent to each other, We're not energetically the same, and it's not a spontaneous symmetry breaking, it's just no symmetry to begin with, or an explicit symmetry breaking. Is there any difference between explicit symmetry breaking and spontaneous symmetry breaking? Yes, there is. There is one phenomena that can happen when there's spontaneous symmetry breaking that will not happen if there's explicit symmetry breaking. The phenomena is called domain walls. A domain wall is what happens if far away out here, very, very far away, you insist along this line here that everybody is heads, and way out here you assume that everybody is tails. Right? What then is the state of lowest energy? And then the state of lowest energy is everybody on this side tails, everybody on this side heads, and a boundary in between where heads go from, where tails go to, from the boundary where you go from tails to heads, called domain wall. So the presence of domain wall, and this would not be the case if you had explicit symmetry breaking. If you had explicit symmetry breaking, then the state of lowest energy would just be all heads, period. Wouldn't care very much that you did this thing over here. So spontaneous symmetry breaking, in this case, the signal of it is the existence under certain circumstances, certain kinds of experimental setups would lead to the existence of domain walls, where on one side you had one thing, on the other side you had the other thing. And so it would be the presence of domain walls which would be the signal that there was a spontaneous symmetry breaking. All right, so this is the basic idea of spontaneous symmetry breaking, a symmetry of the system, but with an instability or an instability that you can kick off by going very far away and just fiddling with something very far away, and that will fix everything. And as I said, the signal or the signature of it is the existence of domain walls. Next time we'll talk about other kinds of spontaneous symmetry breaking and come to the Higgs phenomenon. The Higgs phenomenon is a phenomenon of spontaneous symmetry breaking, and we'll talk about it next time. So just keep this example in mind.
For more, please visit us at stanford.edu.